Welcome to another Guideline Geo webinar. Today we're going to be talking about the GroundTEM Ralli. This is our new mobile TEM system, and we'll look at how the ABEM TEM lineup sits right now that we've added this. We'll look a little bit at TEM theory and specifically how that applies to mobile measurement for people who may be new to the method as well as the product. Then we'll look at a fairly high-level system design of the GroundTEM Ralli and look at how you would purchase the packages that we offer and what accessories go with it. Then probably the most important bit of the presentation is we'll look at how you can choose the right solution. So whether that is a static TEM system or a mobile TEM system, and also whether you would like to apply the use of a mobile TEM system or an ERT system, a traditional resistivity system. And then hopefully at the end, we'll have time for questions. So this is the ABEM TEM lineup as it stands for our static systems. That is the WalkTEM 2 that we launched in 2021, which was, of course, a follow-up to the original WalkTEM, and then the GroundTEM instruments, which we've been adding to over the last year. We started with the i5 and the i10, and then actually just this week released the i20, which is a more powerful unit. And those all sit together quite nicely as a lineup. And now, of course, we are introducing the GroundTEM Ralli. Now, being a mobile system, this isn't really an either-or kind of situation. This is sort of a parallel option to those static systems, because being a mobile system, it actually opens up other application areas. So our lineup comprises of static systems such as the GroundTEM I series and the WalkTEM 2, semi-mobile systems, which would be the GroundTEM with the Explorer coils, these lightweight carry frames where you would take a measurement still in a static position, but you can just pick the whole lot up and move to the new sounding location without having to draw in all of the transmitter loop and the receiver coil and then move to the next location, then lay them back out again. So those are permanently fixed transmitter and receivers on carry frames, and two people can carry that across the landscape relatively easily. And now, of course, we're adding this mobile system, the GroundTEM Ralli. To refresh us or introduce you to the TEM method, I've got just a few short slides. What are the headlines for TEM? Well, we say that it's a non-destructive, rapid tool for the search, mapping and monitoring of groundwater, environmental change and mineral deposits. With static systems, depths of hundreds of meters can be investigated in minutes and work can be finished whilst other survey methods would still be setting up. With a towed system, landscape scale resistivity surveys become a more cost-effective proposal. So what is it we're saying in there? Well, non-destructive, so like a lot of geophysical methods, we were not actually breaking ground. And in fact, this is even less destructive than a traditional ERT measurement because we're not putting any electrodes in the ground. Everything is done with loops and coils sitting at the surface. We're listing a number of application areas there, and the thing that ties them all together is that they are conductive targets. TEM responds to conductive bodies. So that's what we can map directly. We can infer more resistive layers by them being sandwiched between conductive materials. And we're also saying that this is a very fast means of data collection. So if you look at a traditional static TEM system with a transmitter loop laid out, receiver coil at the center, you would create a profile of resistivity against depth. And the nearest equivalent method to give you the same result would be a VES measurement, where we have just 4 electrodes and we gradually move them further and further apart, pushing our focus depth deeper and deeper until we've got to our target depth. Now, the problem with that is that it's a 5-to-1 ratio in terms of the distance between the outer electrodes and the depth that we're measuring at. So to get to 100 meters, you need to have electrodes spread across 500 meters. To get to 200, spread across a kilometer. So it's quite a laborious process, whereas with TEM, you lay those coils out, the loops, the coils, and we can take a measurement in seconds to minutes and have a very deep resistivity sounding. So much, much quicker. With a towed array, it's a different game again. There we are continuously measuring towing behind some kind of vehicle, covering very large areas of ground, which then allows us to actually build resistivity models over large areas to considerable depth in a way that perhaps we haven't been able to before. And we'll talk more about that later. So all TEM systems will have three components. That is something that is transmitting a signal into the ground, either a transmitter loop or coil, a receiver coil there to get the signals as they come back from the ground, and then also an instrument to generate that current pulse around the transmitter and receive those signals that are coming back. Those signals that come back, we convert into an apparent resistivity, and we plot that against time, because in a TEM measurement, that's what we're doing. We're generating a pulse, a transmitted pulse, and we look at the signals coming back from the ground at increasing time offset from that initial pulse. And obviously, the further in time, we assume the deeper that signal is coming from. So we take that raw data, and then we put that in inversion software, and that provides us with a layered model of resistivity against depth. And that model is such that if we recreated the survey we did in the field in that software space, we would end up with hopefully the same raw data. And once we've got the model, then we can start to make our interpretations from that. In a mobile system, there's nothing different really. We would have the instrumentation on the tow vehicle. Then we've got our transmitter configuration, our transmitter setup, and then behind that our receiver coil. And what we do is we run current around the transmitter loop or the transmitter coil. We then, whilst doing that, generate a magnetic field, and that's shown in yellow here. We then switch the current off very quickly, and that magnetic field collapses. As it collapses, it generates eddy currents in the ground, and those eddy currents spin out and downwards with increasing time. And that eddy current spinning out and down is what we call the transient, hence the name transient electromagnetics. Those currents in the ground spinning as they do generate their own magnetic field, which is changing over time, and that is what our receiver coil is picking up. Of course, this is mobile, so we can just repeat that process again and again and again at a very high frequency in order to be able to create series of soundings all in one long profile that we can then also generate a 3D model from if we need to by collecting data across the landscape. This is presenting that process data in its simplest form, where we just keep it as individual soundings, closely spaced, just a few meters between them. And that is what we make our interpretation from. But we can then run processing to create a continuous profile, or as I say, a 3D volume. One thing that we come across in TEM measurements is the compromise of deciding whether we want to put high current round our transmitter and be able to push very deep, or whether we'd like a lower current and be able to see the more shallow detail. And the reason why we have to compromise is because if we use the very high current in black, that high current pulse takes a long time to switch off, and we can't begin measuring the ground signal until all of that current is gone, because the signals we get back from the transmitter are far, far higher than the signals we would expect from the ground itself. On the other hand, if we put a low current through the transmitter, it switches off much more quickly, but that signal will be lost into the background electromagnetic noise that is all around us all the time, much, much quicker, and we don't get that deep information. So we run our instruments in what's called a dual moment measurement, dual current. So it's flicking continuously between high current pulses and low current pulses. And then a high current provides us with the information from depth, and the low current allows us those early times to be measured and gives us that more shallow detail. By combining those both together, we then have one data set to process and inverse, and then that will give us our model to work from. And dual moment is something that we have on all of the ABEM instruments, whether it's the WalkTEM 2, the GroundTEM I series, or the Ralli instrument. So what are the headlines that we give for the Ralli? Well, we say that from a single profile to an entire landscape, the GroundTEM Ralli is the ultimate solution for rapid, high-resolution subsurface mapping of conductive targets. Designed for efficiency, this cutting-edge system, based on technology from our expert partners at TEM Company in Denmark, delivers precise resistivity data for groundwater, geology, and environmental surveys down to 200 meters. There is, of course, the caveat that 200 meters is in the ideal conditions, but that's still, even if we're a little bit shallow of that, it's still pretty impressive for a system that we're able to tow around at up to 20 kilometers an hour. So again, we're highlighting the fact that this is a fast way to collect resistivity data, and so it does challenge ERT. And later in the presentation, we'll compare those two methods to try and give you an idea of when one might be more suitable than the other, and show you what the capability of these mobile TEM systems is. So let's have a look at the system design. Being a TEM system, there are the three components of instrument, transmitter, and receiver. And what we see here is a picture of the instrument itself. So this is housing both the transmitter electronics and the receiver electronics, but they are separated out in this box. Transmitter on one side, receiver on the other. And this will look very familiar if you've seen our I-series instruments. It's the same form factor box, but in this instance, there are actually two that are mounted adjacent to each other. And the reason for that is that this has a 30 amp transmitter, and that's a lot of power to be running inside that box. So we need active cooling. So the second box, as you can see in this smaller image, is actually the cooling system with the cooling fluid and the cooling fan there. And then that is connected through to the electronics in this box to keep everything nice and stable. As with the I-series, we've tried to put information on the sides of the instrument so that you're not always having to reach for a quick guide or a user manual. And this is also run from an app. With this one, we've got a bit more information on the screen when we're running it. So this is recommended to be run from a tablet. But again, there's no great requirement for high spec tablets for this to run. And we'll talk a little bit more about that as well later. Transmitter, this is mounted on sleds, no wheels. It's a sled mounted affair with these wings that are made of fiberglass, and then that carries the transmitter loop or transmitter coil, depending on which configuration we've chosen. Because this is a 30 amp transmitter, we have to run this on a much larger power source. So the recommended power source for this is a 100 amp hour lithium ion battery, and the system comes with a suitcase for mounting that battery in, and then all you have to deal with is plugging the charging unit into one side or taking the power out from it and plugging that into the instrument itself. On the receiver end of the instrument, we have our input for the single receiver channel. And because this is much lower power and because it's on a completely separate set of electronics to minimize any noise or crosstalk, this is running off just a small lithium ion battery, one of those clip in, clip out type batteries. So again, if you've seen our I-series instruments, it's the same form factor battery that is in that box. So what are the options when we come to purchase a GroundTEM Ralli? Well, first of all, the whole system comes in a very neat package whilst we're talking about packaging. In these photos is everything you would need for a survey apart from the tow vehicle. And what you can see is that it's been very neatly designed so that everything fits inside a collared Euro pallet, standard Euro pallet with these wooden collapsible collars on it. So if you've got the smallest sized transmitter configuration, that is a 2x2x1. Everything's in the box. If you use the 3-meter transmitter configuration, then these wings are slightly larger and they just come in a separate case. But otherwise, you can fit everything in this one pallet. So in there we have the receiver platform with the receiver coil mounted on top of it. The transmitter platform, the wings that just slot into these receivers, and then the TX loop or coil, again, depending on configuration, all on that side there. Then we have the battery box that the lithium ion power pack goes into. And then we have our lead-in cables and our tow ropes for the two sleds. The instrument, the tablet that comes with it, and all the accessories are in these black boxes. And again, you can see those are in the palleted case. And the final thing we have is the ATV platform. So this is to make mounting the system on the back of the tow vehicle much, much simpler. It has plenty of strap slots so that you can strap it down to the back of whatever vehicle you're using. And then it has milled inserts there for you to drop the various cases in so that there's no getting it wrong. Everything fits in one place and then you just connect everything up very simply. And there's also positions on here for tie down eyes so that you can then strap the boxes down so nothing's going to slide around or topple off the back of the tow vehicle whilst you're moving across the fields. When a customer comes to buy this, then we will likely ask them which options they would like. With the instrument, it's pretty easy. There's just one instrument. It's the 30 amp dual moment transmitter with the single channel receiver. So that bit, nice and simple, same every time. But the big choice to make is the transmitter configuration. There are three primary choices. That is a 2x2 single turn loop, a 3x3 single turn loop, and a 3x3 3-turn coil. And basically going from bottom to top in this list is increasing the depth that you're able to penetrate with that transient. We then also have a choice of whether you're using regular or extended leading cables, and we'll come back to talking about those when we look at the tow vehicle that we would be using for this system. With the receiver coil, it's a simple choice again because there's only one choice of receiver, and you should pair the lead-in with whatever choice you made for the transmitter. So if you've gone for a regular lead-in on that, then you use a regular lead-in on the receiver, and vice versa for the extended. Of course, you might want to have more than one option available to you. So of course you can add other accessories. So you can add additional transmitter loops, or you could add the other set of leading cables. If you, for example, had bought the 3x3 transmitter loop and you wanted to also add the smaller one, then you would need to also add into that the smaller wings, because the wings are designed to fit either the 3 or the 2 meter square that the transmitter configuration is designed to be. Final thing is the choice of software. And again, there isn't really a big choice here. We have the acquisition app and we have post-processing software. And the acquisition app is the GroundTEM Ralli controller. And this runs on a tablet, as I say, designed to work with older devices. You don't need to have the latest model from Samsung. It will work on a fairly old version of Android. And most of the hard work is actually being done in the instrument itself. We're just configuring, setting up commands, and reviewing the data as it comes in on that tablet. The tablet is there not just to set up the instrument and collect data, it also allows us quality control. So we see a quick snapshot of the health of the instrument. Green is good, red is bad. It tells us which line number we're on. It also allows us to bring in base mapping, which will help us with navigation. The app will also paint swaths so that we can see where we have been and whether we were actively recording data or not at that time. We can start and stop the instrument from here. So it's just a play stop toggle. And normally what we would do is press play, start the instrument running, and just continuously run all through the survey. What we can then do is assign that data to individual profiles by using the start and end line button down here. And that means that when we come to do the post-processing, all of that data set is there if we want to look at any of the data during the day, but it's automatically being chunked into individual profiles, and that makes the post-processing much simpler for us. On the right-hand side, we have more detailed information. So we've got all of the different map layers that we've uploaded to the instrument. So in the middle here, you can see that there's some kind of aerial photograph. We've also got some kind of base mapping, and then we've got polygons in there as well, which have been made transparent so that we can see all of those layers at once. So it's like a simplified GIS. We also have a data tab that gives us sort of the detailed background to the green and red on this left-hand side. And then we can also see the data as it's coming in. So in the current guise, you would see the raw data, the decay curve. So you'd just be looking for that to be nice and smooth, fairly consistent as we drive across the landscape. However, we are at the point of releasing real-time inversion as well, and that will allow us to take a step further. So we're not just looking at raw data as it comes in, but actually looking at the final resistivity models as well, which allows us not only to do QA, QC in the field, be sure that the data we're going to take back and put through our post-processing software is fit for purpose. It allows us, if necessary, to start making interpretations right away. In terms of that post-processing software, we would be recommending Aarhus Workbench. There isn't really a better alternative in the market for processing mobile TEM data. And you may already have a copy of Workbench Essentials. You might be using that for ERT, IP. You might be using it for static TEM measurements. So if you do already have Workbench, then all you need to add in is the Toad TEM module, and then you're a way to go with the mobile processing. Processing of mobile TEM data is a fair bit more complex than static site-by-site measurements. So we do typically recommend having training as part of the purchase package. So what are we towing this system with? It's a mobile system. We have to tow it with something. The most suitable thing is a standard medium-sized ATV quad bike, call it what you will. The reason for that is it has plenty of power to be able to drag the equipment behind it. It's not a particularly heavy system in that regard. But more importantly, it minimizes the amount of conductive material in that tow vehicle. So anyone who has used TEM a lot will know that coupling is a big problem. When we generate that initial signal, we're trying to generate currents, eddy currents, a transient in the conductive parts of the subsurface. The big problem is we also introduce signals into anything else that's conductive around the apparatus, and that includes our tow vehicle. So, for example, we could have horrible what we call capacitive coupling. This is the kind of stuff you quite often get from buried cables and the like, and that is very easy to spot because the data suddenly starts jumping around in a zigzag fashion, oscillating up and down, and we can see immediately that the data are bad. What's worse is when we get what we call galvanic coupling, and that's where we just induce a signal into a loop of metal or a metal surface where the current just keeps flowing round and round until it gradually runs out of steam through heat dispersion. And the problem with that one is that that looks an awful lot like a conductive body beneath the instrument, and the instrument doesn't know where that conductive material is. So that can be a real issue because it could give us a false impression of the conductivity of the ground beneath us. So with a small tow vehicle like this, it isn't an issue. We've got plenty of distance between the apparatus and the tow vehicle to avoid that coupling. However, if we have vehicles that have big roll cages, big metal load beds at the back, or are just much larger vehicles, then we get into the issues of coupling coming in. So for that reason, we have the standard and the extended lead-in cables. And so there is that decision to be made. What is the most likely thing you will be towing this with? In the manual, we give you the instructions on how to do a distance test so that when you do select a vehicle, first thing you do when you get to the field is run the distance test, starting with the vehicle near the apparatus, taking measurements continuously and moving the vehicle further and further away to see where that coupling disappears. And that will give you, hopefully, the confidence that you're using the right cables for that particular vehicle. As I said, probably the most useful part of this webinar is about how you come to choose the method for your particular project. And so we're going to look at the difference between static and mobile measurement, and we're going to look at the difference between mobile measurement and ERT. So first of all, static, semi-mobile, or mobile. So by static, I mean the WalkTEM 2 or the I-series with the 20 meter, 40 meter, or 80 meter transmitter loops. By semi-mobile, I mean the GroundTEM instruments with the Explorer coils. And by mobile TEM, of course, I mean the Ralli. So we would say that static systems are best suited to large-scale prospection, not detailed mapping, but prospection, going out across a large area, doing widely spaced soundings, and then processing that, maybe to get an idea of where to go back and do more detailed investigations. These static systems are, a 1D method. In fact, TEM is always a 1D method, but it's more obvious that it is with these static measurements where you have big distances between the centers of measurement. And that means that we are kind of hamstrung by the 1D considerations, which are that we assume that any target, any layer we see is of uniform resistivity and extends out in all directions to the horizon. So we are best applying these methods to big, broad targets, big, broad aquifers, large mineral bodies, that kind of thing, where by and large, those assumptions ring true. Deep targets. If we want to go deep, then you can't be a static system for that because we can use much larger loops, much higher current, and more importantly, we can leave the thing in one place recording for a long period of time to increase our signal to noise ratio. So we said earlier that the thing that kind of kills the TEM signal is when it gets lost in the background EM noise that's all around us all the time. So if we can measure for longer, repeating over and over again that same consistent signal, then that will gradually superimpose upon itself and the random background EM noise should cancel itself out. And that makes it easier for us then to image those deeper deposits. And of course, budget is not a small consideration. You may not have enough to invest in a mobile system, and then static systems are a much easier point of entry for getting yourself onto that TEM ladder. So you can take a static system and just take lots and lots and lots of measurements and build up a 2D profile, build up a 3D volume, but it's time consuming. But if you have the time and the resource, but you don't have the budget, then maybe that is the best way forward. Mobile systems like the Ralli, they suit large-scale mapping. So now we're looking at more detail because we're collecting much, much more data, more densely spaced data sets with our admittedly still 1D soundings much closer together. But that allows us, when we're processing, to actually take into account what is happening in those adjacent soundings and constrain our inversion and get a more reliable model with more detail from it because we have that extra volume of data available to us. This also opens up TEM to being able to map laterally confined targets. So traditionally, you would say that if your water is contained within an area of fracturing in bedrock that maybe not be very wide, then a 1D method, whether it's VES or TEM, is not ideal because the chances of hitting that and being able to identify it are pretty low and it's quite difficult. However, if you are effectively making continuous measurement, then you can see where that confined area is much more easily and delimit it. And of course, we're talking about using systems with much smaller loops, coils. So therefore, we're talking about shallow mapping. So top 150 meters, you should be safe in any of the larger configurations. With smaller configurations, it might be a bit less than that. And as we said earlier, in ideal conditions, you might be able to stretch that up towards 200 meters, but it's never going to be over that, whereas static systems can take us well beyond. If you are in that kind of, I really could do with that mobile, denser data, but you're also in that camp of not having the budget, then that's where those Explorer coils for the I-series come in, because they do allow you to be much more efficient. You can collect data much more quickly, and you can actually manually build up those profiles and volumes in a pretty feasible way, but without having the budget requirement for a full mobile system. So this is the comparison between a static TEM system and a mobile TEM system. So of course, the mobile TEM is being shown by the background data, the continuous profile. And then in front of that, we have the individual soundings from the static system. And unsurprisingly, they correlate incredibly well together. And so they should. They are the same systems, effectively. They're working on the same methodology, The electronics at the core of it are doing the same thing. We're responding to the geology in the same way. So we would expect them to have good correlation. But in this instance, what the mobile system is doing for us is providing that additional detail. And the big example of that is this buried river channel here, where if we were relying just on these broadly spaced soundings, we wouldn't know it was there. However, by being able to collect data more densely, then of course it appears much more clearly. So we talked about different configurations for the Ralli system. Well, which one are you going to choose? There are three considerations to make here. What are your near surface requirements? Do you need detail in the upper meters? How deep do you need to see? How far do you have to push into the ground? And are there any constraints upon where we're going to be collecting the data? So in terms of near surface requirement, the larger those TX loops are, or if they're a coil rather than a loop, the longer it takes to switch the current off. And so therefore, the longer it takes for us to start the recording measurement, and therefore we lose that near surface information. So it's not as well represented in the final model. So smaller loops are the best option there. Depth requirement, as we said earlier, the bigger the setup, the bigger the configuration, the deeper we'll be able to push. So from the 2x2 single turn up to the 3x3 multi-turn coil, we're gradually increasing the depth. There isn't a nice, easy rule of thumb to use with TEM when you're trying to estimate what the maximum depth you'll achieve is. We use these rules of thumb for VES and for ERT, and they are flawed in themselves because they are so dependent upon system configuration and also the geology. But with TEM, it's kind of a step further. We're even more reliant upon the mix of geology that we're working over when it comes to the differences in depths that are achievable. And in fact, one of the next data examples will show that quite nicely. So really what we say to people is, if you have a particular depth requirement, really the best thing you can do is model it. So model the geology that you think you'll be working in and the target you're going after, model the configuration you're planning to use, and see whether you can resolve that feature or not. And then the final thing is the deployment constraints. If we use those larger loops or coils in the transmitter configuration, our sphere of influence that we'll get coupling within increases. So we need to be further away from infrastructure, whether that's buildings, cables, pylons, fence lines. We need to get further away. So we might be on smaller sites, and so then a smaller system is better. Or it might be that there are physical constraints. It might be that we're working between trees and we know that a 3-meter wide loop isn't going to fit, or gateways that you can't fit a 3-meter wide loop through. And so a smaller one is more preferable. So looking at the difference between two of the different configurations, on the top here, we have a profile with a 3x3x1. So 3x3 single loop transmitter coil. And what you see are the individual soundings that were made whilst the whole array was being pulled across the site. And the darker color is where we have high confidence in the model result. Then the paler colors are where we have a lower confidence in the model, and then we have our maximum DOI defined as where that model stops. And what we've done is we've taken the confident layer, and we've overlaid that on data from the 3x3x3, so the 3-meter 3-turn coil, transmitter coil. And what we see is that it does increase the depth, but not by very much. And the reason for that is that this base layer in this particular example is very conductive. And a transient is lazy as soon as it gets into a conductive layer. It just hangs around and doesn't want to push much deeper. So although we've added to the strength of the original signal, we're not getting much deeper. In this instance, it's exactly the same thing. We've got the same two configurations, but here the basal layer has higher resistivity and the transient will move faster through those resistive base layers. So what we see is, here's our limit of confidence with the 3, 3, 1. Here's that same confidence layer compared to the 333, and we get a much greater DOI, much greater depth where we have confidence in the model, and that's because that transient is continuing to move through this slightly more resistive base unit. Final one is comparison between a mobile TEM system and Terrameter LS2, Ralli or LS2. This is an obvious question to make because all of a sudden we're producing a 2D resistivity profile that looks an awful lot like we would get out of our ERT system, but we've done it by driving across a landscape rather than laying out a number of electrodes and then running through all of those different combinations. So in general, ERT systems provide better near-surface resolution. Your electrodes plugged into the ground, you can get good detail almost immediately from that system. We have much better representation of higher resistivities with an ERT system. So by that, what I mean is when a TEM signal, a transient encounters a high resistivity layer, it can't really determine, when you come to do the inversion, you can't really determine whether it's 1,000 ohm meters, 2,000, 5,000, 10,000. The confidence, the fit of that model won't really change as you change those resistivities. So it's very difficult to say what the absolute resistivity might be. You just see that it is more resistive than the material surrounding it. With ERT, we're able to tie down that resistivity much more closely. Obviously, having a system like an LS2 opens up other applications. So it's an alternative way, a very good way of collecting IP data. We can do borehole measurements. We can set the things up for remote monitoring. You know, there are these other applications, whether it's lab measurements or field measurements, that we could be doing with that system. And then finally, something you don't often get to say about an ERT, an imaging resistivity system, and that is that it's actually a cheaper point of entry than a mobile TEM system. So we can, you know, specify a 2D ERT system that is, you know, cheaper than a mobile TEM. However, mobile TEM systems do allow us to map resistivity on a landscape scale in a way that just probably wouldn't be efficient or cost effective with traditional ERT. It gives us much better depth penetration if we've got a particularly resistive overburden. So if the top layers are resistive and then underneath that we have something conductive, if you're using an ERT system, that resistive top layer will choke the amount of current that we can push into the ground. And that means that we will lose our signal much more quickly. The potential field will disappear and we won't have a particularly great voltage to measure and disappears into background noise. TEM, the transient, will move very quickly through that resistive layer, hit the conductive layer and hang around and allow us to see it much more easily. And we also have that ability to resolve conductive targets a bit better than we do in ERT. So if we're looking at the difference between fresh, brackish and saline water, that's pretty easy with the TEM system, whereas sometimes with ERT systems, it can be quite difficult to get a good, reliable estimate of the lower resistivity layers. So some examples here. On the top, we have a profile collected with a mobile TEM system, and on the bottom, profile collected with ERT. And the scales are all the same: vertical scale, horizontal scale, and the resistivity scales. They're identical between the two plots. And what we see is that by and large, they're showing us the same thing. They're showing us that there is a high resistivity band through the middle here. That below that, there's something much lower resistivity. And then between the high resistivity band and the surface, there's a slight drop off in that resistivity. The mobile TEM system is showing us more detail in that lower unit. It's showing us more variation in that lower resistivity unit. Conversely, it's not showing us a great deal of detail in terms of absolute resistivities for that middle layer. So you can see that it's resistive. So as long as you know what the geology is, that's all well and good. But with the ERT system, we're getting closer probably to what the true resistivity of that layer is. And you can see here that, you know, you're talking about maxing out this resistivity scale in the ERT profile, but not being close to it with the TEM. Again, with the near surface, we see that the ERT is delivering us a little bit more information there. Again, as expected, because we have that slightly better near surface resolution. Now, this plot is a little bit unfair because the ERT data hasn't been blinded. And by blinded, I mean cut off at the point where we think the model is becoming unreliable, whereas the TEM data has. So you would probably find that the DOI on this would be somewhere through here, and more comparable to what's on the TEM system. Here's another data set doing exactly the same thing, same horizontal, vertical, and resistivity scales being used. And in this instance, what we can see is that we have, again, very similar overall interpretation of there being some higher resistivity near surface, a kind of concentration of higher resistivity that's been interpreted as a buried river channel, and then a much lower resistivity base unit, which here would be an underlying clay. So what are the differences? Well, again, the ERT is providing us with more near surface information. It is defining the extent of that buried river channel a bit more tightly because it's dealing with that higher resistivity a little bit better. And it's giving us a bit more information about higher resistivity variation in that mid area. However, the mobile TEM system is punching much deeper. And that's because the ERT has been choked a bit by the higher resistivities at the surface. That's reducing the amount of current we can inject, whereas the TEM spinning through that really nice and quickly and then getting down to the conductive material beneath. So we see a greater depth with the mobile TEM system. The other thing that TEM is doing for us is it's helping us with that interpretation of where is the top of the clay. So with the ERT, it's a little bit blurred. We've got this kind of full rainbow splurge, for want of a better technical term, between the higher resistivities and the low resistivity base unit. So where do you draw that line? Do you draw it at the edge of the blue, through the green, through the yellow? Whereas in the TEM, we can refine that difference where it's a relatively sharp boundary between the top of the clay and probably glacial tills that are overlying it. So it makes it much easier for us to make that interpretation. One final thing about the comparison between ERT and mobile TEM, and that is the areas in ERT where we don't have great reliability on the model, and that is in these corners. So when we have our rectangular plot like this, we have very low sensitivity down in these corners because of the way the potential field is spread out when we're using those 4 electrodes to collect our data points. So here we can consider that in these regions, we get an impression of what the resistivity is doing, but we don't have any particular great confidence in those areas. But if you're taking a TEM measurement, let's not forget, this is a series of 1D soundings. So we have a good, reliable model from meter 0 all the way through to the end of that profile. Admittedly, the stuff in the middle, when we do the post-processing, we have a greater confidence in it because we can use this ability to look at the data on either side and constrain the inversion. But if we've got a deep sounding over here, the stuff at depth is going to be more reliable than the stuff at depth in an ERT measurement, where we need to make sure that our target feature is somewhere within or closer to the middle of our profile. And of course, the final thing, as we keep talking about, is the ability to do landscape scale survey. So in this instance here, we've got 940 hectares of survey with 25-meter line spacing, and this was achieved in 10 days. And the data can then be processed either as individual 2D profiles or, as we've done here, taken into one big block and then sliced horizontally to give us resistivity maps at different depths. So we've got 5 to 10 meters, 25 to 30, and 50 to 60 meters here. I think anyone who's ever done any ERT would understand that trying to do something on this scale would just be impractical and incredibly expensive. So for us to go out, certainly at 25-meter line interval, and recreate this data set, it would be some mammoth undertaking, and it would certainly be taking more than 10 days. So again, that's one of those things that the mobile system brings to the fore for us. So that's everything I wanted to talk to you about. If you do have any questions, you can either contact me directly, jimmy.adcock@guidelinegeo.com, or contact our sales or support teams at sales@guidelinegeo.com or support@guidelinegeo.com, and we'll answer any questions that you have. So thanks very much for attending, and I hope to see you in another one of these very soon.